Today we'll start looking at what are called rational functions. So let's start by defining them. A rational function is a quotient of polynomials denoted f of x is equal to n of x divided by d of x. And we call them this since the top is the numerator and the bottom is the denominator. And these can be any polynomials whatsoever with one exclusion. D of x must never equal 0. Since we can't divide by 0, we need to make sure that that's the case. And similarly, we can see that the domain of our rational function is all real numbers except for the x values that make the denominator 0. Remember, we're never allowed to divide by 0. So we need to rule these cases out. So for most of this, we'll be looking at the interesting parts of the graphs of our rational functions. And we'll actually see what happens when we try to divide by 0 and the mess that that causes. So let's begin by looking at the simplest rational function, which is f of x is equal to 1 divided by x. It's two polynomials. X isn't equal to 0, and so we can find our domain easy. This is all real numbers except 0. And we can write this as negative infinity to 0, union 0 to infinity. And we know what the graph of this looks like. It's these two pieces, where on the left, it's negative and it goes down to negative infinity. And on the right, it comes down from infinity and it reaches 0. Now we ask ourselves, okay, we see this 0 is a bad part. In general, what does the graph look like when we get close to our bad point? In this case, x equals 0. Just by looking at the function, it's normally not very clear. So what we have to do is we have to pick two x values to the right and left of our bad denominator points. Normally we want them to be pretty close. So let's do that and see what happens. So I'm going to pick some x points and see what their y points are. Let's pick one to the left of 0. Meaning this is a negative number that's just a little bit smaller than 0. So how about negative 1 over 10? When we put this into the function, f of x is equal to 1 divided by x, it just flips whatever number we put in and spits it back out. So this becomes negative 10. Similarly, if we input negative 1 divided by 100, it flips it over and it becomes negative 100. And if I tried putting in negative 1 divided by 1000, same thing, flips it over and it becomes negative 1000. So here, it's going to negative infinity pretty quickly. And we see this in the graph here. Once we get close to the y-axis, we start dropping down and down. We reach negative infinity as we get very, very, very close to 0. Now, on the other hand, what happens if we're a little bit to the right of 0? It means we're a fraction that's just a little bit bigger. We can play the same game, plug in 1 over 10. That'll give us 10. 1 over 100 gives us 100. And 1 over 1000 will give us 1000. So these numbers go to infinity very quickly. So on the other side, if we look at the graph here, when we get close to our bad point, 0, we go up and up and up and we eventually reach infinity. Sometimes they both go to negative infinity, sometimes they both go to positive infinity, or they can flip-flop. The only way we can really check this is by plugging these numbers in and seeing what we get. Now we call these by a special name. Lines that sort of divide or separate our graph into pieces we call asymptotes. And they occur in two different forms. They occur around our bad denominator points, and they occur as x goes to infinity and negative infinity. So let's see these on our graph here. If we look, our bad denominator is x equals 0, and if we mark this in here, we can think of this as a brick wall that our graph has to swerve to avoid. It can't ever touch the brick wall, it just has to start driving alongside of it. Since these are straight up and down lines, we call these vertical asymptotes. And normally, any time that we have these bad denominator points, we'll have a vertical asymptote. So for this graph, it occurs at x equals 0. And we see we've divided our graph into these nice two pieces, the negative part and the positive part, but we actually have one more division as well. If we look as x goes off to infinity, why don't we change colors here? Out this way, and negative infinity out this way, it seems like they're approaching some nice lines as well, and they are. It's almost like a tractor beam has sucked our graph and is going to hold on to it as x stretches out further and further and further. And we call these, let me fix this here, horizontal asymptotes. They're horizontal lines that act as tractor beams, and as x travels further and further out into space, it sort of grabs onto them and it doesn't let go. So for this graph, our horizontal asymptote is y equals 0. And again, we see we've divided this as sort of the negative piece on bottom and the positive piece on top. Now our graph can pass through horizontal asymptotes. They only take effect once we get out really far into space here. Okay, so let's give some nice formal definitions for our asymptotes, and then we'll see them in action. So the line x equals a is a vertical asymptote of the graph f of x when the y values of our function go to positive and negative infinity as our x values approach some nice number that we normally call a. So these are the brick walls that occur on very specific spots where our graph swerves to avoid it. We say the line y equals b is a horizontal asymptote of the graph f of x when our y values approach b as our x values get bigger and bigger and bigger in the positive and negative direction. So again, these are tractor beams. As x travels out further into space, the y values settle onto this nice b value and never coast away. We can also sort of think of it as cruise control for the y values. So let's try finding these, and we'll graph f of x is equal to x plus 1 divided by x squared minus 4x minus 12, and see if we can figure out what's going on here. So remember, the first step is we always need to throw out these divide by 0 points. So step 1 is we take the denominator, we set it equal to 0, and we factor. So two numbers that multiply to be negative 12 and add to be negative 4 are negative 6 and positive 2. So this becomes x minus 6, x plus 2 is equal to 0. Negative 6 times 2 is negative 12. Negative 6 plus 2 is negative 4. And this means that the 0 of our polynomial will occur at x equals 6 from the first part here, and x equals negative 2 from our second term here. And the graph should have vertical asymptotes, these values here. Now let's start by throwing these on, and then we'll see what it looks like. There we go. Here's our x-axis. And quickly, maybe we can note, if we set the numerator equal to 0 and solve for that, this will give us our zeros of our function. And it also helps us graph down, since now we can say, okay, at -1 here, we're going to have to hit the x-axis. And at -2, we're going to have a brick wall. And at +6, we're going to have another brick wall. Okay, so what does it look like in the middle here? Well, the only real way we can tell is by grabbing points that are close to our vertical asymptotes and plugging them in. So let's plug in a couple values here. So if x equals -2 is a vertical asymptote, we should plug x equals -2.1 and x equals -1.99 into our function and see what the y values are. If we plug this into the polynomial, we'll get that for x equals -2.1, y is equal to -12.609, and for x is equal to -1.99, y is equal to 12.390, and now we have the shape starting to take hold. When we're to the left of our asymptote, we're in the negative direction, and when we're to the right, we're in the positive direction. Now let's do this again for x equals 6, and how about we do it in another color here? If x equals 6 is a vertical asymptote, then we should check some number like x equals 5.99, and x is equal to 6.01. Okay. If x is equal to 5.99, y is equal to -87.484, and if x is equal to 6.1, y is equal to 87.516. And again, we know how this will behave around our vertical asymptote now. When we're smaller than 6, we're in the negative direction here, and when we're bigger than 6, we'll be positive. The last thing we need to check is our horizontal asymptotes. So let's draw a line here. For horizontal asymptotes, we just need to plug in some pretty big positive and negative x values. So let's plug in x equals 100 and x equals -100. For this case, if x equals -100, y is equal to -0.10. Other way around. If x equals -100, sorry, y is equal to -0.010. And if x equals 100, then y is equal to 0.0105. And it looks like these are heading towards y equals 0. And so we'll have a horizontal asymptote at the x-axis here. Once we've found these points, we just need to connect our graph with some straight lines. So it gets real close to the x-axis here, and then it swerves down to -infinity. On the other side of the brick wall, it comes down. It's going to pass through the x-axis at -1 here, and then it's going to swerve back down to -infinity. And on the other side of our second brick wall, it comes down from infinity and goes off and settles right on the x-axis at y equals 0 there. These couple points completely determine what our graph's going to look like. Now, all of the details might not be there, but on the other hand, we at least have a very nice picture of what it should look like, and we can see how the vertical and the horizontal asymptotes are at play. So let's look at a couple rules here. We don't always need to plug in values for all of our asymptotes, and we can see pretty easily, especially for our horizontal asymptotes, what they're going to look like. So let's say we have a rational function, f of x is equal to n of x over d of x, where our leading coefficient on top is an, and our highest power is n, and on the bottom, our leading coefficient is bm, and our highest exponent is m. These n and m can be completely different numbers, and in general, we expect them to be. So for this to work, we need to make sure that our numerator and denominator have no common factors. If we factor them down completely, they don't have any zeros in common. Those are other potential bad points that we'll deal with in the next lecture. Now the graph of f of x will always have vertical asymptotes at the zeros of d of x. We can always draw our brick walls in if we know where the denominator is equal to 0, again, as long as we have no common factors. This is the best we can do. In general, we always have to plug a number in and see if it's going towards positive infinity or negative infinity, but our zeros can help us out a little bit. On the other hand, our horizontal asymptotes are quite simple. F of x has 1 or 0 horizontal asymptotes, which we can determine by comparing the degrees of the numerator and the denominator. We check to see how n and m are related. Are they bigger, smaller, or equal? When the top degree is smaller than the bottom degree, then the graph of f of x has the line of y equals 0 as a horizontal asymptote. And this is just like 1 over x has this horizontal asymptote. So it doesn't matter how much bigger the denominator is, as long as m is some larger number, we'll always have the same asymptote, which is quite nice. On the other hand, if the degree of the top and the bottom equal each other, then we have a bit of a weird horizontal asymptote. We have a horizontal asymptote at the line y is equal to an divided by bm. Now these are the same leading coefficients right here. So we take the first numbers and we divide them by each other, and that becomes our new horizontal asymptote. And if we want to think of this, this is sort of like the line 1 over 1, or 2 over 1, or 3 over 5, any nice straight line, which is just a simple number. The final case is when the top is bigger than the bottom, and if n is greater than m, then the graph has no horizontal asymptotes. And this is just like the graph of y equals x, or y equals x divided by 1. This is a straight line that goes up and down forever, and it never really settles in and goes on cruise control. And so we have a nice formula for the horizontal asymptotes. It just boils down to these three cases, and there's not anything tricky about them. Simply look at what the biggest exponent is on top and bottom, and then compare them with these three rules.